The universe is expanding, and we are measuring that expansion. Through distant galaxies, pulsating stars, relic radiation from the Big Bang, we watch space itself stretch. We listen to the echoes of the beginning. Yet the number we get, the expansion rate, the so-called Hubble constant, refuses to settle. Two of the most reliable measurement methods disagree by several percent, a difference that should not exist if our cosmological model is complete. It is as if the universe tried to read its own barcode, only to find that the lines do not match. What if this conflict is not a measurement error, but a sign of something deeper? Could the cosmos itself be signaling a gap in our understanding of time, space, matter, energy? And if so, what does that mean for our place in the universe, and for the universe's place in us? We begin with the fact: the universe expanding, measured, known. Then we turn to the origin of that measurement, the methods, the instruments, the data points. We move from what we observe to how we observe, from the measurement to the mechanism. In that shift lies the beginning of the tension. Let us leave behind the comfort of a single number and step into the process of measurement itself, into the scaffolding of observation, into the interplay of light, distance, time. And then we will reach the point where conflict appears. The story begins with a simple observation. Distant galaxies are moving away from us. Their light stretches as it travels, sliding to the red end of the spectrum, carrying the signature of expansion. This is not an interpretation. It is not a model. It is the direct imprint of motion on light. A century ago, telescopes revealed patterns that quietly rewrote our sense of the universe. Galaxies farther away receded faster. The relationship was steady, predictable, almost elegant. Expansion seemed to follow a rule, and that rule became the Hubble constant, a number meant to fix the universe's pace. But every number is a doorway. Once measured, it demands to be measured again, and the more precisely we looked, the more the doorway seemed to split. We now measure the expansion rate in two independent ways. One method looks at the nearby universe, stars, galaxies, supernovae, objects close enough that their distance can be mapped step by step. The other method looks at the oldest light in existence, the cosmic microwave background, the faint radiation released when the universe was young and hot. These two approaches should converge, because they are measuring the same universe, but they do not. Their disagreement is small in everyday terms, yet enormous in scientific terms. The numbers differ in a way that cannot be dismissed by chance. The universe measured through nearby stars expands faster. The universe measured through ancient light expands slower. Both methods are reliable, well-tested, and independently confirmed. The tension is not in the tools. It is in the cosmos. Imagine walking into a room lined with mirrors. You see yourself reflected from two angles. Both images should match, but one is subtly stretched, as if the geometry of the room is hiding an unseen curve. That is the position cosmology finds itself in today. For a moment, step back and picture the nearby universe. Clusters of stars, spiral arms, dust lanes glowing in infrared. Each serves as a rung in a ladder of distance. At the bottom are pulsating stars whose rhythm correlates with their true brightness. Compare their real and apparent brightness, and you know how far they are. Climb higher, and supernovae act like cosmic flashbulbs, marking distances across tens of millions of light years. With enough measurements, you can map the expansion in the local universe with remarkable precision. Now shift to a different kind of vision. Erase stars, galaxies, all current structures. See only a uniform bath of microwaves, light released nearly 14 billion years ago. Subtle temperature variations in that light trace the early distribution of matter. From that pattern, one can infer how the universe must expand over billions of years to reach the cosmos we see now. It is a deep backward calculation, tracing growth from infancy to adulthood. These two visions, near and far, should overlap like two halves of a single map, but the seam does not align. The closer method gives a larger number for the expansion rate. The early universe method gives a smaller number. Between them lies a gap that does not shrink with improved data. It is an unusual feeling when a scientific field reaches this point. Data becomes too consistent to ignore, yet too discordant to reconcile. The tension does not fade, it sharpens. Every measurement carries a kind of personality. Some whisper hints. Others speak in steady, unwavering tones. The Hubble tension speaks with two voices that are both confident and incompatible. We stand between them, listening. There is a quiet human truth here as well. We often assume the universe is coherent, that its rules will align cleanly when seen from different angles. But the cosmos is under no obligation to match our expectations. When we listen carefully, it sometimes reveals complexity disguised as simplicity. Imagine holding two clocks. One is built from nearby celestial distances, ticking according to the motion of present-day galaxies. The other is built from the relic glow of the early universe, ticking according to primordial conditions. Both clocks keep perfect time within their own systems, yet when you compare them, they drift apart. That drift is the anchor of this story. It tells us that something, in measurement, in physics, or in our understanding, is incomplete. And incompleteness in science is not a flaw. It is the spark that drives discovery. Look again at the night sky. Stars shimmer slightly as the atmosphere moves. Galaxies form faint smudges, quiet and distant. Nothing about that view suggests conflict. But embedded within the starlight are clues that challenge our deepest theories. Light arriving from millions of light years away is indifferent to our interpretations. It brings its data, its timing, its shifting colour. We assemble those signals into knowledge, and when that knowledge fractures, we must follow the fracture to its source. You might think the disagreement is small enough to ignore, but in cosmology, small differences can point to vast territories of new physics. A subtle mismatch in expansion could hint at unknown forms of energy, variations in fundamental parameters, or processes in the early universe that have left no other trace. We stand at the threshold of such possibilities, calm, patient, attentive. As the universe expands quietly, endlessly, it leaves behind a trail of signals. Each is a reminder that we are still learning how to read its story, and sometimes the story contradicts itself. The tension is real, the conflict is measured, and the universe, in its vast silence, continues to stretch. We breathe with it. To understand why the universe disagrees with itself, we must look closely at how each measurement works. Not just the instruments, but the logic behind them. The expansion rate is not something we observe directly. It is inferred from light, motion, and distance, each measured in layers. Those layers form two independent paths, and each path carries its own internal consistency. Begin with the nearby universe. Here, distance is the central challenge. The cosmos does not come with markers or rulers. We rely instead on objects whose brightness or behavior reveals how far they must be. These are called distance indicators, and they function like stepping stones across space. The first stones are pulsating stars, especially a group known for their predictable rhythm. Their brightness rises and falls with a period that encodes their true luminosity. By comparing that intrinsic brightness to what arrives at Earth, we determine distance. It is similar to recognizing a lighthouse by the pattern of its beam, even when fog softens the glow. With thousands of such stars mapped, astronomers calibrate the next set of indicators, supernovae. These powerful explosions, though varied in nature, include a subclass that reaches nearly the same peak brightness. They serve as beacons across hundreds of millions of light years. A ladder is built. Stars calibrate supernovae, supernovae calibrate galaxies, and galaxies reveal the local rate of expansion. This ladder has been refined over decades. Every rung is checked with independent datasets, new telescopes, and revised models of stellar evolution. Its strength does not lie in a single measurement, but in the interlocking structure. If one rung were flawed, the rest would show strain, yet they align with remarkable stability. Now turn to the second method, where distance is not measured, but modelled from early universe conditions. The cosmic microwave background is ancient radiation that fills all of space. Its faint temperature variations carry information about the density, composition, and geometry of the young cosmos. By analysing those patterns, scientists reconstruct the conditions at the universe's beginning. They then evolve those conditions forward using the standard cosmological model. The resulting prediction includes the expected expansion rate today. This process is not guesswork. It is anchored in decades of observations. From satellite missions that mapped the microwave background with increasing precision, the early universe behaves like a resonant structure, with sound waves frozen into the plasma that once filled all of space. Those frozen patterns act like fingerprints, allowing us to infer how much matter existed, how radiation behaved, and how quickly space expanded in its infancy. When these two methods were still coarse, they appeared to agree, but as precision increased, the difference emerged and sharpened. The nearby universe consistently gave a faster expansion rate. The early universe consistently gave a slower one. To understand why, imagine two clocks again. One clock is local, built from stars and supernovae. The other is ancient, built from early cosmic vibrations. Both clocks keep time within their own systems, but they are not built from the same components. One responds to present-day structures, the other responds to primordial physics. A thought experiment helps clarify the distinction. Picture holding a balloon with tiny dots drawn across its surface. As you inflate the balloon, the dots move apart. If you measure their separation now, using a ruler laid across the surface, you get one value for the rate of expansion. But if someone told you the exact conditions just after the balloon was formed, the temperature, the distribution of dots, the thickness of the rubber, you could model how fast it must be expanding today. If the modeled rate disagrees with the measured rate, the discrepancy forces you to question your assumptions about the balloon's material, the air inside, or the history of its inflation. The Hubble tension is precisely this moment of questioning. It is the recognition that our balloon model, though elegant and consistent, might be missing an ingredient. Before diving into what that missing ingredient might be, we must understand why each approach is trusted. Every distance indicator in the local universe is cross-checked. Infrared observations reduce the effect of dust. Parallax measurements from space-based observatories anchor the distances with geometric precision. Supernova catalogues span decades, ensuring the calibration remains stable. Likewise, the cosmic microwave background is mapped with extraordinary fidelity. Its temperature variations are measured at tens of millions of points, each point contributing to a statistical portrait of the early cosmos. The model used to interpret that portrait has passed countless tests. It predicts galaxy clustering, gravitational lensing patterns, and the distribution of elements from the first minutes after the Big Bang. When two systems as robust as these disagree, something fundamental is at stake. Either new physics is required, or a subtle assumption has misled our interpretation. A quiet reflection emerges here. We expect the universe to behave consistently, yet consistency is a human expectation, not a cosmic rule. Sometimes, the universe hides complexity in places that seem simple. Sometimes, a number refuses to converge because the truth beneath it has not yet been fully revealed. Light from a nearby supernova carries the story of the present universe. Light from the cosmic microwave background carries the story of the young universe. Two stories, separated by billions of years, now meet in our equations. And their meeting is uneasy. You can imagine these signals as two beams crossing in a dark room. One beam warm, immediate, filled with structure. The other ancient, cool, nearly uniform. Where they overlap, the tension appears, sharp and unmistakable. We stand at that crossing, listening to both beams at once. The mechanism of each measurement is sound. The disagreement is not a flaw in their design. It is a doorway to deeper understanding. And the doorway is beginning to open. The tension becomes a paradox, the moment both measurements are accepted as true. Not provisionally true, not tentatively true, but solid within their own domains. Each method stands on independent foundations, yet they lead to incompatible conclusions. A universe measured nearby expands faster. A universe measured through ancient light expands slower. The same cosmos, two answers. Paradox arises when logic folds back on itself. Here, the fold appears because both methods trace the same history, one from the present backward, the other from the past forward, and the histories do not meet cleanly in the middle. To see this conflict clearly, imagine two historians reconstructing a life. One begins with recent memories, interviews, photographs. The other starts with birth records, childhood events, early influences. If both historians are careful and well-trained, their narratives should converge. But if the adult's life story does not seem consistent with the documented childhood, the inconsistency forces deeper questions. Is a piece of information missing? Is the interpretation incomplete? Or is the subject's life stranger than assumed? Cosmology now occupies this position. The universe's childhood and its adulthood no longer connect with the smooth arc predicted by established theory. The paradox sharpens when we consider timescale. The early universe was hot, dense, and governed by physics we understand with some precision. The present universe is cold, sparse, and shaped by the accumulated effects of dark matter and dark energy. Yet the laws linking these eras should be universal, steady, and unchanging. If the laws haven't changed, why does the expansion rate appear to diverge? A subtle unease emerges when a system resists reconciliation. It suggests that the gap is not in the data, but in the framework used to connect the data. A framework can be accurate for a long time before reaching a point where its limitations reveal themselves. The Hubble tension may be such a point, a quiet fracture spreading through a long-trusted structure. Consider a moment inside a planetarium. The lights dim, stars bloom across the dome, and galaxies drift outward in simulated expansion. The motion feels smooth, continuous. But imagine if the projector system ran two programs at once, one showing a universe expanding at one speed, another showing it expanding at a different speed. On the surface, the images might appear identical at the beginning and end, yet their internal timing would drift apart. That drift is the essence of the paradox. Galaxies today appear too far apart for the slower expansion predicted by the early universe. Or, conversely, the early universe appears not to have expanded quickly enough to reach the distances we observe now. From either viewpoint, the mismatch remains. This conflict forces attention to places we normally treat as stable. Distance indicators, early universe models, the composition of matter and energy, all are potential sites of hidden complexity. A paradox is not a failure, it is a contour revealing where understanding becomes thin. As the paradox unfolds, human intuition encounters a boundary. We like stories where causes lead clearly to effects, but the universe does not promise that clarity. Instead, it offers signals that sometimes align and sometimes refuse to align, leaving us suspended between interpretations. In a quiet room, place two metronomes on a wooden board. Start them at slightly different tempos. At first, their ticks overlap, then drift, then fall into rhythmic tension. Two steady beats, each internally consistent, refusing synchronization. The Hubble tension is a cosmic version of that demonstration. Two measurements, each precise, falling out of sync as precision improves. An emotional mirror moment appears here. We often search for simple explanations, but the universe invites us to accept complexity. It demonstrates that knowledge is not a straight path but a braided one, where strands split and rejoin. This tension is one of those splits, a moment where divergence reveals something hidden. Light drifts across space, carrying a history that is both fragile and enduring. Nearby galaxies whisper one value, ancient radiation whispers another. Between them hangs a quiet contradiction, suspended like two notes forming a dissonant chord. Dissonance has power. In music, it creates expectation, a need for resolution. In science, it triggers curiosity, the urge to explore what must change for harmony to return. But unlike a musical chord, the universe does not shift to satisfy us. It holds the tension and waits. As we examine this paradox, the mind naturally moves toward questions that stretch beyond observation. What if the universe evolved differently than we assume? What if dark energy changed over time? What if new forms of matter influenced early expansion? These ideas are not conclusions, they are invitations. The paradox does not point in a single direction, it opens a landscape. Step into that landscape for a moment. Imagine drifting between galaxies, far beyond the influence of any star. The darkness is almost complete, yet faint light from billions of sources converges around you. In that quiet, the scale of expansion becomes tangible. Space itself grows beneath you, stretching without motion, without sound. And in that stretching lies the paradox, subtle, persistent, waiting to be understood. Two truths held at once. Two histories that should align but do not. A universe that measures itself through light, yet fails to agree with its own measurement. This is the heart of the Hubble tension. A conflict not between instruments, but between eras. Not between scientists, but between the universe's own narratives. When reality speaks with two voices, the task is not to silence one of them. It is to learn why the voices differ. And the answer, whatever it is, will reshape how we understand space, time, and the quiet forces that guide the cosmos. The paradox remains unresolved. But resolution is not the purpose of this moment. Recognition is. We stand inside the tension, calm, attentive, listening to the universe disagree with itself. When a paradox holds its shape, the next step is insight. Not the final answer, but the shift in perspective that allows new questions to form. The Hubble tension is not a puzzle to be solved in a single move, it is a doorway into deeper structure, the hidden architecture guiding how the universe evolves. To reach that insight, we begin with a simple recognition. Both measurements reflect truths about different epochs of the cosmos. Light from the early universe carries information about high-density conditions, rapid interactions, and uniformity. Light from the nearby universe carries information about structure, complexity, and the accumulated influence of billions of years. We are not comparing like with like. We are comparing youth with age. And yet, the universe's laws should bind these eras seamlessly. That seamlessness is what breaks. One line of thought suggests the early universe may have held extra ingredients, not visible matter, not dark matter as we understand it, but additional forms of energy or particles that influenced early expansion and then faded. If true, the ancient light would encode a slower expansion because it was shaped by a different physical environment. The present-day universe, lacking those ingredients, would naturally expand faster. Another line of thought rests on the idea that dark energy, the driver of modern acceleration, may not be constant. If dark energy changed over time, even slightly, the expansion history would bend in ways our current model cannot capture. Early expansion might appear slower because the later acceleration was stronger than expected. And a third line of thought points inward, toward the structure of matter itself. If the behavior of neutrinos or certain exotic particles differs from our assumptions, the inferred expansion from the microwave background would shift. A small change in a particle's properties could ripple across billions of years. Each possibility holds merit. None yet stands above the rest. It is tempting to leap toward the most dramatic explanation, to imagine a universe filled with undiscovered components or evolving forces. But insight in science grows by careful accumulation. We do not discard the familiar, we extend it. We do not assume the extraordinary, we test what makes the ordinary insufficient. Stand for a moment on a quiet shoreline. Waves move in steady rhythm, each shaped by conditions far away. Wind, depth, distant storms. Looking only at the nearest waves tells you one part of the ocean story. Looking at the distant horizon tells you another. When those stories conflict, the reason often lies in forces you cannot see from where you stand. Cosmology faces a similar horizon. The early universe speaks through patterns frozen when atoms first formed. The nearby universe speaks through light shaped by stars, galaxies, and expanding space today. Insight comes from recognizing that these two stories are not meant to be identical. They are meant to be compatible. The tension marks where compatibility fails. One insight rises clearly. The universe may be more dynamic than our standard model allows. If expansion cannot be linked smoothly across cosmic history, the laws we use may need refinement. Not replacement, refinement. A subtle shift in timing. A small correction, a deeper layer. Imagine drawing a curve through 2 points. If the points do not align perfectly with the predicted arc, you adjust the curvature. Perhaps the slope is different. Perhaps the starting conditions changed. The new curve must still respect the points, they anchor reality, but its shape reflects a more accurate relationship. The Hubble tension forces such a recalibration. Here, a quiet human mirror comes into view. We often assume knowledge grows linearly, that understanding accumulates without resistance, but discovery rarely follows straight lines. It moves through tension, through conflict, through the realization that what once seemed complete is now only a foundation. We too evolve by confronting the gaps in our understanding. Insight also comes from what the tension cannot be. Extensive reanalysis has shown that systematic errors, flaws in calibration, dust effects, supernova variability, cannot explain the discrepancy entirely. Even if minor corrections are needed, they are not enough to erase the gap. That endurance strengthens the case that new physics may be involved. Visualize a narrow beam of light cutting across a dark room. Dust particles flicker in the beam. You can correct for the dust, filter the noise, refine the measurement, but if the beam itself bends ever so slightly, the correction will never resolve the shift. You must question what is bending the beam. That is where insight grows. A deeper question appears. Is expansion truly uniform across time? Our model assumes it is governed by smooth, predictable influences, but what if some process changed between the early and late universe? Not dramatically, just enough to alter timing. A universe with evolving dark energy or changing gravitational behavior could naturally produce the observed tension. This does not mean gravity changed everywhere. It may mean gravity behaved slightly differently under early universe conditions. Insight often reveals itself through opposing statements. Both can be true, and together they shape the boundary of possibility. The universe is consistent in its laws. The universe may require new laws to explain its own consistency. Hold those two sentences for a moment. The first grounds us. The second opens the future. In scientific inquiry, tension is not an obstacle, it is a signal. The gap in expansion rates is not noise in the data. It is a clue, a quiet pointer toward missing structure. As we examine that clue, a sense of calm returns. The paradox is no longer a rupture. It is an axis around which new knowledge can grow. We stand on that axis, looking outward and inward at once. Light from the nearby universe tells us where we are. Light from the ancient universe tells us where we came from. Insight lives in the space between. We listen. The universe stretches. And in that stretching, a new understanding begins. The second block begins with a return to observation, because every deep question in cosmology starts with light. Light is the messenger that crosses billions of years to reach us, unchanged in its message, even as everything around it evolves. Among its signals, one feature stands out with particular clarity: the stretching of wavelengths as the universe expands. This stretching is not metaphor. It is not an analogy for motion. It is the direct evidence that space itself is growing. Look at a distant galaxy. Its emitted light leaves in one wavelength and arrives in another, shifted toward red. The amount of shift tells us how much the universe expanded while the light was in flight. And that shift becomes a tool, a cosmic measurement that allows us to trace motion across unimaginable distances. Now picture a sequence of galaxies at increasing distances. Each galaxy's redshift increases. Each represents a deeper window into time. Plot those redshifts against distance, and the slope of the relationship gives the expansion rate. This relation was the foundation of the first expansion measurements. It remains the backbone today. But with higher precision, the relationship becomes more than a straight line. Subtle deviations appear, not noise, structure. These deviations reveal how the universe's expansion has changed over time, slowing under the pull of matter, accelerating under the influence of dark energy, and eventually settling into the rate we measure today. In the nearby universe, these deviations are mapped with extraordinary detail. Galaxies in clusters, galaxies in voids, galaxies at the edges of filaments. Each region carries information about local gravitational influences and global expansion. A careful observer can separate these effects, isolating the expansion component from the internal motions of galaxies. A single image from a next-generation telescope shows thousands of galaxies, each an anchor point in a three-dimensional map of space-time. Their collective motion forms a pattern like currents in a vast ocean. Some currents flow faster, others slower, but together they create a tapestry revealing the universe's recent expansion history. Now shift scale again. Look at galaxies not individually, but collectively, millions at a time. Their arrangement is not random. They cluster at a preferred scale, a remnant of early universe sound waves that rippled through hot plasma before atoms formed. These frozen waves create a statistical feature called a standard ruler, imprinted across the cosmos. By measuring its apparent size at different distances, we track how the expansion stretched space. This ruler provides an independent check on local measurements, and once again, it supports the faster expansion rate found through nearby galaxies. Two methods within the late universe now align, reinforcing each other. Yet, the early universe method remains firm in its slower value. Two truths, locked in place. Before we follow that conflict further, pause for a moment and imagine drifting outward from the Milky Way. Go beyond its spiral arms, past its halo of old stars, into the darkness where galaxies become isolated islands. In that silence, expansion becomes almost tactile. Distances increase not because objects move through space, but because space itself grows between them. You float in a region where galaxies appear to recede evenly in all directions. No drift, no preferred direction, just steady, quiet expansion. This is the anchor experience behind all expansion measurements. It tells us the universe is not expanding like an explosion with a center. It expands everywhere at once, a property of space rather than motion. From this anchor arises a subtle truth. Every measurement of expansion is a measurement of the universe's history. Redshift captures the accumulated effect of billions of years of stretching. Distance captures the structure that formed within that expansion. Together, they form a timeline, a record of how the cosmos changed. But the timeline splits. One branch describes a universe that stretched more slowly at early times and now expands at a modest pace. The other describes a universe that stretched smoothly into a faster present. Both branches fit their own evidence. Both branches interpret light correctly within their domains. A reflection forms gently here. We assume a single cosmic story, but the data invites two narratives. Each narrative is incomplete without the other, yet they refuse to merge. As you imagine holding these two timelines side by side, a sense of quiet wonder emerges. Not confusion, wonder, because disagreement at this scale hints not at error, but at depth. It means the universe is not simplistic. It means the cosmos carries layers we have not yet peeled back. One more detail anchors our understanding. The expansion rate is not a static property. It changes as matter dilutes, as radiation cools, and as dark energy asserts influence. We measure these influences across epochs, mapping how the universe transitioned from being matter-dominated to being dark energy-dominated. This transition is well established. The tension does not arise from the transition itself. It arises from how the timing of that transition differs in the two measurements. This timing discrepancy is more than a number. It represents a possible misalignment in the fabric of cosmic history. Light carries the imprint. We carry the interpretation. The difference between the two is where new knowledge may emerge. We stand again at the cosmic shoreline. Waves of light arrive from different depths of time. Some waves reflect the calm cadence of nearby galaxies. Others reflect the deep, ancient rhythm of the early universe. Their patterns do not match, and within that mismatch lies the anchor of discovery. The universe continues expanding, quietly, endlessly, and we continue listening, assembling its story, one signal at a time. To understand why expansion looks different from one cosmic era to another, we have to examine how the universe keeps time, not through clocks or calendars, but through the motion of matter and the flow of light. Every structure in the cosmos, from stars to clusters to the faintest ripples of early radiation, marks a moment in that unfolding timeline. Begin with the late universe, the realm of galaxies and large-scale structure. Here, gravity is the sculptor. Matter pulls together, forming clusters, filaments and walls. Between them lie immense voids, regions nearly empty, where expansion proceeds with fewer interruptions. Galaxies inside filaments experience two kinds of motion. One motion comes from expansion, the uniform stretching of space. The other comes from local gravitational pulls. Separating these components requires careful modelling. The expansion forms the broad trend, while internal motions add scatter. Astronomers correct for these effects by measuring thousands of galaxies at various distances and averaging over regions large enough that local motions cancel out. What remains is the clean imprint of cosmic expansion. Another tool comes from the clustering of galaxies at the standard ruler scale. This scale was set when the universe was young, when sound waves rippled through hot plasma, compressing and rarefying matter. When the universe cooled enough for atoms to form, those ripples froze into place. Billions of years later, their imprint still shapes how galaxies arrange themselves. Measuring the apparent size of this frozen ripple at different distances reveals how much the universe expanded between then and now. The ripple acts like the tick marks on a cosmic ruler. If the expansion sped up or slowed down, the observed size of the ripple changes accordingly. This method, called large-scale structure mapping, adds a powerful constraint, and it agrees with the faster expansion rate measured from nearby galaxies. Now turn to the early universe. Its mechanism is different because its physics is different. When the universe was young, it was hot enough that matter and radiation behaved like a single fluid. Photons scattered constantly off electrons, preventing light from travelling freely. In this dense environment, sound waves propagated through the plasma, creating rhythmic compressions. These compressions left temperature variations in the cosmic microwave background. The size and amplitude of the variations encode the physics of that early fluid: density, pressure, composition. By studying them, scientists infer conditions at the moment when photons finally decoupled from matter and began travelling unimpeded. From that starting point, cosmologists evolve the universe forward. Matter clumps. Radiation cools. Dark energy eventually accelerates expansion. The entire sequence is governed by a set of equations that track how the energy content of the universe changes over time. The predicted expansion rate today is a direct outcome of this evolution. It arises not from one piece of data, but from how all pieces fit together. To see the difference between the methods, imagine two travellers navigating the same landscape. One begins at a mountain peak and traces their way down through valleys and forests. The other begins at the coastline and climbs inland. If the map is correct, their paths should meet precisely in the middle. If they do not, either the terrain is different from the map, or the map is missing features. Cosmology is holding two paths that refuse to join. One natural question is whether the early universe model is too rigid. It assumes that certain quantities, like the density of dark matter or the speed of sound in the early plasma, are fixed. But what if one of these parameters was slightly different? Even a small shift could alter the predicted expansion rate. Another possibility lies in the geometry of space. Not curvature in the usual sense, but subtle geometric effects that influence how light travels over large distances. If photons took slightly different paths than assumed, our inferences from ancient light could be biased. But each time cosmologists test such adjustments, they find that the early universe model resists modification. Its predictions match many independent observations: galaxy clustering, gravitational lensing, the distribution of light elements. Changing one part often breaks another. This resistance is striking. Meanwhile, local measurements also resist reinterpretation. Parallax distances anchor the first rung of the cosmic ladder with geometric certainty. Infrared observations minimize dust. Supernova light curves are modelled with decades of accumulated detail. Any systematic error large enough to shift the expansion rate would have to appear in multiple steps, yet no such pattern emerges. Stand back and picture these two frameworks as vast scaffolds built around the same structure. Each scaffold is stable on its own, but where they overlap, the beams do not line up. The discrepancy is not in the scaffolding, it is in the structure itself. Here, a thought experiment illuminates the situation. Imagine two people measuring the height of a tower. One starts from the ground, using a ladder with evenly spaced rungs. The other lowers a rope from the top, marked in intervals. If the rope and ladder disagree, the tower's interior might contain a twist or tilt, not visible from the outside. A quiet reflection arises here. The universe does not hide information out of mystery. It hides it out of scale. Processes too subtle or too ancient leave traces only when our measurements become precise enough. The Hubble tension may be such a threshold. The moment when precision reveals structure we did not know to look for. As the mechanisms of measurement become clearer, the tension between them becomes sharper. Not a flaw, a guide. We listen, patient, to the difference between ancient and nearby light. We watch how structures form and how radiation cools. We trace the timeline of expansion with two tools that refuse to converge. And in that disagreement, the mechanism of discovery gains momentum. A paradox grows sharper when every path toward resolution closes. By this point, both early and late universe measurements have been tested, reinforced, recalibrated, and expanded. Neither collapses under scrutiny, neither drifts toward the other. The gap remains steady, like two parallel lines that should meet at the horizon but never do. The paradox begins with a simple expectation. If the universe follows consistent rules, then measurements made from different eras should converge, but the cosmos refuses that convergence. Its early expansion appears slower, its recent expansion appears faster. A single history becomes two incompatible arcs. Imagine standing at a long, straight railroad track. In the distance, the tracks seem to meet, a visual convergence shaped by perspective, but if those tracks represent the early and late universe, you walk toward the meeting point and discover that the lines never actually cross. The illusion dissolves, the separation persists. In cosmology, this separation is not an illusion. It is a measurable, repeatable fact. To understand the depth of the conflict, picture the early universe again. a dense, hot sea of light and particles. Sound waves ripple through it, imprinting their rhythm on matter and radiation. This rhythm becomes the blueprint for the cosmic microwave background. Its peaks and troughs encode the universe's initial conditions with exquisite precision. Now picture the late universe. Galaxies drifting apart. Supernovae flashing across billions of light years. Gravitational structures forming a cosmic web. These structures evolve from the same initial conditions. They should carry a compatible signature of expansion. But they don't. When we compare the blueprint to the structure, the mismatch stands out like a building whose foundations predict one height, yet whose top floor ends at another. A paradox is born not from contradiction, but from compatibility that fails in a specific, persistent way. And this failure grows clearer as precision increases. Light from the early universe tells us that the universe should expand today at one pace. Light from the nearby universe tells us it actually expands faster. The paradox is not that one must be wrong. The paradox is that both appear right. An emotional mirror rises here. In our own lives, we sometimes hold memories that do not align with later events, not because the memories are false, but because the context has changed in ways we did not witness. Something shifted in the middle, between then and now. The Hubble tension echoes that experience on a cosmic scale. To probe the paradox further, imagine a long corridor illuminated by two lights. One light shines from the far end, ancient and cool. The other shines from behind you, warm and recent. Their beams overlap in the middle, creating a region where shadows and reflections blend. If the lights are slightly different in color or intensity, the overlap reveals the difference unmistakably. Cosmology stands in that overlap. The early light and the late light illuminate the same universe, but they do so with different hues. Neither can be dismissed. Neither can be forced to match the other. The paradox deepens when we consider the paths each measurement takes. The early universe path is global and predictive. It models the cosmos from infancy, projecting forward through billions of years. The late universe path is observational and cumulative. It builds from nearby structures outward, step by incremental step. These paths are fundamentally different ways of knowing. When different methods converge, confidence grows. When they diverge, understanding expands, not through clarity, but through tension. A thought experiment clarifies the structure of this tension. Imagine reading two versions of the same biography. One follows the subject's childhood, tracing influences and early events. The other follows the adult life, documenting choices, relationships, and achievements. If both accounts are thorough, they should align. But if the adult behavior seems inconsistent with the childhood context, something is missing. Not from the accounts, but from the story that connects them. The universe's story seems to have such a missing chapter. Another layer of paradox emerges from the stability of the measurements. The early universe expansion rate is anchored by an enormous data set, mapping temperature variations across the entire sky. These variations are consistent across multiple missions. The late universe expansion rate is anchored by geometric distances, supernovae, and galaxy clustering, all converging on the same faster value. This dual stability generates a strange tension. If both sides are stable, but incompatible, then the instability must lie in the connection between them. That connection is the cosmological model, the framework linking early density, matter content, dark energy, and expansion history. When a framework is near its limits, paradoxes appear not as errors, but as signals. They show where the model bends under the weight of precision. The Hubble tension is one such signal. Step into the paradox for a quiet moment. Imagine floating in intergalactic space, where galaxies drift like lanterns on a dark ocean. Their recession feels steady, calm, almost meditative. Now imagine the early universe filling your field of view, a bright, dense fog pulsing with primordial sound waves. The contrast is overwhelming, yet both visions describe the same cosmos. Holding them together reveals how profoundly different the universe was across time. The paradox is not simply that two numbers disagree. It is that two eras, governed by the same fundamental laws, appear to evolve into incompatible presents. This realization opens a conceptual fissure. Either something unknown shaped the early universe, altering the rhythm of its expansion, or something is shaping the present universe beyond what we have accounted for. Both possibilities are profound. Neither can be dismissed. The paradox reaches its full height here. It is not a contradiction. It is an open question that cuts into the structure of cosmic history. And in that cut, new physics may be waiting. We listen to the tension. We stand in its outline. The paradox holds steady and unresolved, pointing toward a deeper layer of reality. Insight begins with the recognition that paradox is not a boundary. It is an opening. The Hubble tension does not indicate that cosmology is broken. It indicates that cosmology is ready to grow. To move through that opening, we examine what the tension teaches, not what it resolves. Insight often appears in the form of constraints rather than answers. Each constraint narrows the space where new physics may hide. The first insight is that the early universe may contain additional components we have not yet detected. These components must affect expansion strongly at early times, but fade or transform as the universe cools. Candidates include new forms of radiation, light particles, or interactions that briefly altered the balance of energy. If present, they would shift the pattern of the early cosmic microwave background, lowering the predicted expansion rate. Once they vanish, the universe would settle into a faster, late-time expansion, matching local measurements. This scenario paints a universe with a more dynamic childhood than previously imagined. A second insight points toward the possibility that dark energy itself may not be constant. The standard model of cosmology assumes that dark energy behaves uniformly across time, exerting the same influence from billions of years ago until now. But if dark energy evolved, even subtly, the expansion history would tilt. Early expansion could appear slower, while late expansion quickened in ways we have yet to understand. Here, a quiet shift occurs. Dark energy may not be a single quantity, it may be a process. A third insight arises from examining the behavior of gravity. Gravity is well tested in the solar system, but its behavior at cosmic scales remains a frontier. If gravity acted slightly differently in the early universe, perhaps through additional fields or altered interactions at extreme densities, the inferred expansion rate would change. The late universe, dominated by dark energy and structured matter, might follow modified rules that produce the faster expansion we measure today. These scenarios share an underlying pattern. They require physics that becomes visible only when precision reaches a certain threshold. The Hubble tension may mark that threshold. Now step into the human mirror for a moment. We are accustomed to thinking of the universe as a stable, predictable environment, governed by laws that never shift. But knowledge grows by discovering where those assumptions are too narrow. We do not lose clarity when the universe becomes more complex. We gain it. Understanding deepens when familiar rules meet unfamiliar conditions. Insight into the tension also grows from the structure of the disagreement. The early universe value is anchored in patterns spread across the entire sky. The late universe value is anchored in direct distance measurements and evolving structure. Because these methods probe different regimes of physics, the tension reveals where the connection between regimes may be incomplete. This completeness, or lack of it, becomes its own form of knowledge. Consider another perspective. Imagine a bridge connecting two islands. One island represents the early universe, the other represents the present day. For decades we believed the bridge between them was smooth and well mapped. Now the tension shows that the bridge may dip or bend at a specific point. The islands themselves are stable, the path between them needs revision. That revised path could take many forms. Some theories propose early dark energy, a temporary energy field that accelerated expansion in the first few 100,000 years, leaving signatures in ancient light while fading before later structures formed. Others propose additional neutrino-like particles affecting early density. Some suggest modified gravitational interactions that only appear at extreme temperatures. Each proposal reflects a piece of insight. The tension points toward physics that becomes relevant only when we examine the timeline of expansion with extreme precision. Visualize a dim corridor, illuminated by signals from two epochs. The ancient light reveals the start of the corridor in great detail. The nearby galaxies reveal the end. The middle remains shadowed. Insight tells us that the unseen region, the transition zone, may contain processes we have yet to uncover. Another insight emerges from what the tension cannot be. It cannot be fully explained by dust, calibration errors, or observational biases. Extensive testing has shown that even generous estimates of systematic uncertainty cannot remove the conflict. When both sides of a paradox resist collapse, the paradox becomes a guide rather than a problem. Hold for a moment two opposing statements that frame the boundary of understanding. The universe has a consistent expansion history. The measured expansion history is inconsistent. Between these statements lies the terrain where new knowledge grows, a visual pulse here. Imagine a ripple moving across a still lake. If you track the ripple's motion from two different viewpoints, one from the surface, one from below, you might record slightly different speeds. Those differences would not indicate the ripple is flawed, they would indicate the medium is richer than assumed, shaped by depth, currents, and unseen layers. The Hubble tension is such a ripple, not a mistake but a sign that the medium, the universe, contains layers beneath the surface of established theory. Insight also takes the form of humility. Cosmology operates across scales far beyond human intuition. We are reading signals cast across billions of years, interpreting patterns shaped by conditions we cannot recreate. Yet, through careful analysis, we extract structure and history from faint light. The tension is a reminder that precision does not always yield closure. Sometimes it yields openings. In the quiet space of reflection, one more insight appears. A universe that disagrees with itself is a universe revealing something new. The discord between eras is not chaos, it is information. We stand within that information, aware that the next steps require new ideas, new models, and new ways of connecting the universe's youth to its present. The tension shows where the map fails. Insight shows where the next map will begin. The universe expands. Light carries its memory. And in that memory, we discover the shape of questions we have yet to answer. To begin the third block, we return once more to the observable universe, the domain where light, structure, and motion create a record we can examine directly. Every new measurement strengthens the anchor we stand on, and every anchor brings clarity to the tension that follows. The expansion of the universe is not inferred from a single type of object. It is a collective truth emerging from countless independent signals. Galaxies recede, supernovae brighten and fade. Cosmic structures stretch as space grows between them. Each of these processes contributes to the map of the nearby universe, revealing how expansion behaves today. Consider the role of supernovae once more, because they remain among the most reliable distance indicators in the modern cosmos. When a certain kind of star reaches a critical mass, it ignites in a thermonuclear flash. Its brightness rises rapidly, reaches a near uniform peak, then decays in a predictable curve. These explosions become markers across hundreds of millions of light years. Using them, astronomers create a three-dimensional lattice of distances, woven through thousands of galaxies. Place this lattice beside the redshift of each galaxy, and a clear expansion pattern emerges. Further galaxies recede faster. The slope of the pattern is steep, revealing a faster expansion than that predicted by early universe models. This is not an isolated result. It is repeated through surveys that span decades. New telescopes refine the measurements, but the underlying trend remains. The nearby universe expands faster than expected. Alongside supernovae, another class of objects provides an independent confirmation: pulsating stars. Their rhythmic brightening and dimming offer a direct link between period and intrinsic luminosity. This link is as close as cosmology comes to a cosmic heartbeat. Each pulse marks the exact brightness the star should have, allowing distance to be measured directly. These stars anchor the first step of the cosmic distance ladder. From them, supernovae inherit their calibration. From supernovae, galaxies inherit theirs. Every rung is connected, forming a chain of reasoning that climbs outward into the universe. This chain is not fragile. It is reinforced by geometric measurements from space-based observatories that determine distance through parallax, the apparent shift of stars as Earth moves around the Sun. Parallax is geometry, not interpretation. It anchors the entire system with unwavering precision. Step back and visualize the nearby universe as a dynamic landscape. Clusters of galaxies gather like islands, linked by filaments of matter. Between these islands lie vast voids where expansion is unopposed. The overall pattern forms a cosmic web stretching across billions of light years. Seen from above, if such a vantage were possible, the universe would resemble a vast, interconnected scaffold, blowing softly with distant starlight. That scaffold expands. Its nodes drift apart. Its voids widen. This is not motion through space. It is motion of space. Light from distant galaxies lengthens as the universe grows beneath it, and that lengthening is measurable. We stand on this observational foundation with confidence. The late universe reveals a fast expansion rate, And every tool we use to probe it, pulsating stars, supernovae, large-scale structure, reinforces the same value. Before moving deeper, pause for a brief visual moment. Imagine drifting in space near a quiet galaxy cluster. Each galaxy is a swirl of stars, dust and gas, glowing softly against blackness. Between them lie thousands of light-years of silence. From this vantage, expansion is invisible, yet its influence accumulates in every beam of light traveling toward you. Light arrives stretched, calm, and faintly cooled by the journey. In that faint shift, expansion leaves its signature. This is the anchor fact we return to. Space grows, light stretches. The nearby universe expands faster than the early universe predicts. Now look beyond the galaxies to the distribution of cosmic structures. On the largest scales, galaxies cluster at a preferred distance, the echo of early universe sound waves frozen into matter. This preferred scale, measured across millions of galaxies, confirms the faster expansion rate as well. It aligns not by design, but by physics. The convergence is striking. Independent methods, independent data, independent telescopes, all pointing in the same direction. As we collect these signals, a reflection emerges. We are accustomed to the idea that deeper views of the universe reveal earlier epochs, and that earlier epochs help explain the present. But here, the present challenges the past. The nearby universe speaks loudly, and its message does not fit the early universe prediction. This divergence does not weaken the anchor, it strengthens it, because the tension comes not from uncertainty, but from certainty that fails to align. One more element intensifies the anchor: gravitational lensing. When light from distant galaxies passes near massive structures, the path bends. The amount of bending reveals how matter is distributed. These measurements, combined with galaxy surveys, confirm the rate at which structures grow, and that growth matches the faster expansion rate implied by local distances. The lensing does not lie. It traces matter with exquisite precision, mapping the universe like a fingerprint etched in light. And that fingerprint matches the late universe expansion. Now hold that thought. The nearby universe is mapped. Its expansion is known. Its structures speak with a unified voice. The conflict is not here. It lies in the bridge between here and the early cosmos. The part of the timeline where our model stitches two eras together. This is where the next subphase will turn. The universe expands. Quietly. Endlessly. Light carries its memory, and the memory refuses to match the past we expect. We breathe, and the cosmic story deepens. To understand why the nearby universe shows a faster expansion, we need to look closely at how structures evolve over time. Not the structures themselves, the galaxies, clusters and filaments, but the laws governing how they form and how their growth interacts with expansion. Because the late universe does not simply expand, it expands while gravity sculpts, slows and redirects matter. Begin with gravitational pull. In the early universe, matter was nearly uniform. Tiny variations in density amplified over billions of years, collapsing into galaxies and clusters. This growth of structure depends on two competing forces: gravity pulling matter together and expansion pulling space apart. The faster expansion becomes, the harder it is for gravity to form new structures. Today, when we measure structure growth, we find that galaxies and clusters formed at a rate consistent with a universe that has been expanding faster in its later stages. This is one of the strongest confirmations of the late universe value of the expansion rate. The pattern of clustering, lensing, and galaxy motion all reflect the tug-of-war between gravity and expansion, a contest the universe has been playing for billions of years. Now look at cosmic voids. These vast, nearly empty regions behave differently from dense areas. With little matter to anchor them, voids expand more cleanly, tracing the global rate. Their shapes and sizes reveal how much space has stretched. Deep surveys show that voids today are larger than expected under the slower expansion predicted from early universe data. Their size tells a consistent story. Expansion has been brisk in recent cosmic time. Another layer of mechanism comes from galaxy velocities relative to cosmic expansion. Galaxies have their own motions, drifting due to gravity even as expansion pushes them apart. If the expansion was slower, galaxies would have more time to collapse into clusters. If the expansion were faster, their motions would reflect the pull of gravity struggling against that acceleration. Measurements of these motions, sometimes called peculiar velocities, match the faster expansion value. Step deeper into the mechanism by looking at large-scale structure surveys that map millions of galaxies at different cosmic distances. These surveys calculate how galaxies cluster on scales of hundreds of millions of light-years. From this clustering, we extract something subtle: the rate at which fluctuations in matter grew over time. This rate depends not only on the density of matter, but on the expansion history that either aids or resists gravitational collapse, and the growth rate points toward a faster expansion today. So the mechanism is clear. Late universe data tightly interlocks expansion with the formation of structure. If one changes, the other must change with it. Their agreement strengthens the faster rate. Now shift to the early universe and examine its mechanism once more. We are dealing with a cosmic fluid dominated by radiation and matter locked together. Photons scatter off electrons, creating pressure that pushes against gravity. This interplay generates sound waves whose imprints later shape everything we observe. When photons finally decouple from matter and the universe becomes transparent, these ripples freeze, forming the blueprint from which early expansion predictions are made. The mechanism for predicting today's expansion rate is as follows. Measure the scale of these primordial ripples. Use the composition of the early universe to model how expansion should evolve. Extend that model forward. Extract the current expansion rate. This mechanism is elegant, consistent, and independently verified. Yet it conflicts with the late universe mechanism, which is anchored not in prediction, but in direct measurement. A thought experiment highlights the difference. Imagine two musicians tuning a single instrument. One listens for harmonics produced by plucking a string lightly, the ancient sound patterns. The other listens for the instrument's current tone when struck firmly, the modern resonance. Both methods reveal true information about the instrument, but if the instrument has subtly changed, wood settling, strings loosening, the harmonics and the present tone might not agree. Neither is wrong. The instrument evolved. If the universe evolved in a way not captured by our model, the early harmonics would predict one expansion, while the current tone reveals another. This possibility forms a bridge between mechanisms. The late universe measures what expansion is. The early universe predicts what expansion should be. If is and should be diverge, the mechanism of evolution, the entire middle portion of cosmic history, demands revision. Here, a quiet reflection appears. We often understand processes by their endpoints, but in cosmology, the middle matters. The transition from radiation-dominated to matter-dominated to dark energy-dominated regimes shaped expansion in ways that small model assumptions can magnify across billions of years. Another mechanism enters: the behavior of dark energy. In standard cosmology, dark energy is treated as something steady, but if its influence grew earlier than expected, or changed subtly over time, the universe could shift from slower early expansion to faster late expansion more sharply. This idea is not speculation for its own sake. It is a natural extension of the fact that dark energy is still one of the least understood components of the cosmos. Imagine the universe as a vast fabric on a loom. The early universe sets the initial weave. Late universe structures tug and stretch the threads. Dark energy pulls from the edges. If the pulling force changes even slightly, the entire arrangement of threads shifts, subtly, but enough to alter the measured expansion. Finally, gravitational lensing adds one more layer. Light bending through massive structures traces how matter clusters and how space curves. These curves match the late universe expansion rate, not the early universe prediction. This means the mechanism by which matter influences light confirms the faster rate. The mechanisms stack, they reinforce, they converge, and they diverge from the early universe path. The universe speaks through its structure, and the structure tells us something changed between then and now. We listen to that change. We stand inside its unfolding, and in the quiet gap between prediction and observation, the next insight waits. A paradox becomes clearer when every reinforcing detail makes the disagreement sharper instead of softer. By now, each mechanism in the late universe, structure growth, gravitational lensing, void expansion, galaxy clustering, aligns with the faster expansion rate. Each mechanism in the early universe, primordial ripples, ancient density ratios, temperature patterns in the cosmic microwave background, aligns with the slower rate. Both sides are internally coherent, both sides are externally consistent, and yet they cannot both describe the same unaltered history of expansion. This is where the paradox thickens. Paradox emerges not when data contradicts itself, but when two consistent truths refuse to meet. The universe offers two such truths: the truth of its early rhythm, the truth of its late drift. Between them lies a silent divide, a place where our model does not have enough structure to bridge the distance. To visualize this divide, imagine a violin being played across a long hall. Near the instrument, the sound is complex, harmonics dancing atop the fundamental tone. Far from the instrument, the sound is smoother, shaped by the room and distance. If two listeners record the sound from opposite ends of the hall, their recordings will differ. If the hall is perfectly understood, the recordings can be reconciled. But if the hall contains subtle architecture that neither observer can see, a hidden alcove, a tilted panel, a curve in the walls, the recordings diverge in ways neither listener can explain from their vantage alone. Cosmology stands in such a hall. Early light carries the harmonics. Late light carries the smoothed signal. Both are accurate, both differ. The hidden architecture lies somewhere in between. The paradox intensifies when we consider time. The early universe expansion rate is anchored in conditions from nearly 14 billion years ago. The late universe expansion rate reflects conditions shaped by countless transformations across that vast span. If the laws were constant, the two measurements would join like arcs of the same curve, but instead, they bend away from each other. It is here that the paradox becomes emotional in its own quiet way. We expect continuity. We expect the universe to follow a single story from beginning to now. When that story splits, even slightly, we feel the strain of two histories pressed into one. Now imagine the cosmic timeline as a long thread stretched across a table. At one end, the thread is tight, straight, uniform, precisely mapped by the ancient radiation. At the other end, the thread is looser, shaped by galaxies, structures, and the accelerated expansion we witness today. If the thread were untouched between the ends, the segments would align, but pull gently in the middle, twist slightly, or add a knot too small for the naked eye, and the ends shift relative to each other. Neither segment is wrong, the connection between them changed. This is the paradox. The universe's two ends do not meet cleanly. Galaxies drift apart faster than the early universe predicts. The early universe predicts an expansion that modern data cannot accept. The model connecting the two is elegant, but perhaps incomplete. A deeper layer of paradox arises when we realize how robust the conflicting results are. The early universe measurement is not based on a single observation, but on millions. Temperature patterns measured in different frequencies, different instruments, different missions, all support the slower expansion rate. The late universe measurement is not based on a single technique, but on a web of methods: parallax, pulsating stars, supernovae, lensing, void sizes, all supporting the faster rate. It is extremely rare for two such independent structures of evidence to diverge with increasing precision. Usually, precision resolves disagreement. Here, precision deepens it. Consider a calm thought experiment. Two scientists reconstruct the path of a river. One starts at the river's spring, marking its flow through narrow channels and rocky tiers. The other begins at the delta, tracing broad currents where the river meets the sea. If the terrain is perfectly known, their maps should overlap. But if the terrain contains a hidden channel or an unseen diversion, the two paths differ slightly, each correct within its own domain, each incompatible with the other. The Hubble tension suggests such a diversion in cosmic history. Something altered the flow between the early and late universe. The paradox is not the divergence, it is our lack of a visible cause. Hold the paradox for a moment in stillness. Imagine floating in the darkness between galaxies. Ancient photons glide past you from the edge of time, carrying the slow rhythm of the early cosmos. Nearby galaxies drift in the opposite direction, carrying the fast rhythm of the late cosmos. You are suspended at the crossroads of two tempos, listening to both at once. Nothing about this moment feels chaotic. It feels layered, structured, waiting. In this paradox, the universe is not broken. It is revealing a missing chapter. It is showing us where the thread of its history slips out of view. The paradox does not close doors. It points toward new ones. We stand inside a universe that measures itself and fails to agree with its own measurement. That failure is not a flaw. It is the outline of something deeper, and the outline is beginning to sharpen. Insight begins where the paradox stabilizes, not when contradiction disappears, but when the shape of the contradiction becomes clear enough to examine. The Hubble tension has reached that point. Its boundaries are defined. Its internal logic is fixed. Now we can ask, what does this disagreement teach us about the universe? The first insight is that the cosmos may contain more physical structure in its early phases than our standard model accounts for. This is not speculation born of desire, it is inference born of mismatch. If the early universe held additional energy components, subtle, transient, and gone long before galaxies formed, the cosmic microwave background would record a slower early expansion. As these components faded, the universe would accelerate more rapidly than predicted, producing the faster late-time expansion we observed. This scenario is often called early dark energy. It is not a fully formed theory. It is an idea shaped by constraint, something small, active only at young cosmic ages, influencing expansion without leaving obvious later traces. This insight does not answer the tension. It frames where an answer might live. A second insight comes from examining the nature of dark energy itself. For decades, dark energy has been treated as a simple, constant influence, an ever-present push that accelerates expansion. But if dark energy evolved over time, even subtly, the expansion history would shift. A slightly weaker early dark energy and a slightly stronger late dark energy could bend the expansion curve enough to reconcile the two measurements. This does not require abandoning the framework, it requires refining one of its deepest assumptions. A quiet reflection arises here. The universe often appears simplest when we lack the precision to see its texture. When resolution increases, simplicity becomes layered. Dark energy may not be a static background. It may be a field with its own history, slow, smooth, but real. A third insight comes from gravity. We treat gravity as a constant messenger linking matter to motion, but gravity has been tested in the solar system, around binary stars, and in galaxy rotation, not at the extreme densities of the early cosmos, nor at the enormous scales of the late cosmos. If gravity behaves slightly differently across these regimes, the expansion inferred from early light could differ from the expansion measured from late structures. Such modifications need not be large. A tiny shift in how gravity responds to density could ripple across billions of years. This possibility is less dramatic than it sounds, and more profound. It suggests that the universe's connective tissue may have subtleties hidden from everyday experience. Now step into a visual moment. Imagine a sheet of fabric suspended in a quiet room. Shine two lights across it, one from far away, one from very near. If the fabric has a slight warp, the distant light reveals one curvature, the near light reveals another. Neither light lies. The warp only becomes visible through comparison. The tension. A fourth insight emerges from examining the timeline between early and late epochs. We tend to think of cosmic history as a smooth progression, but physics may contain transitional phases, brief shifts in density or interaction strength that alter expansion without leaving dramatic signatures. These cosmic transitions would act like hidden gears in a machine, rarely noticed, but essential to the way motion changes from one stage to the next. If such a transition occurred, the early universe would naturally predict a slower expansion, while the present would demand a faster one. The mathematics is complex, but the insight is simple. A small shift in the middle of cosmic time can explain a large mismatch between the ends. Another insight comes from what remains stable in spite of the tension. The standard model of cosmology successfully predicts the distribution of light elements, the clustering of galaxies, the patterns of gravitational lensing, the temperature fluctuations in the microwave background. The model is solid at both ends. It is the connection between ends that invites revision. This stability allows us to say something important. The tension does not destroy the standard model. It points to the next layer beyond it. Hold here two opposing sentences that frame the knowledge gained so far. The universe follows consistent laws across time. Our model of those laws may be incomplete across time. Both statements stand. Together they sharpen the path forward. Insight deepens further when we consider the role of precision. A decade ago, the tension did not exist. Measurements were too coarse to reveal disagreement. As precision increased, the expansion rates separated, then stabilized into their current mismatch. This stability is an insight in itself. It tells us the tension is not noise, it is structure, a calm reflection. In science, stability of conflict is often the first sign of new physics. Now imagine a quiet vantage point between galaxies. Light from the early universe arrives with its slow rhythm. Light from nearby structures arrives with its fast rhythm. Hold both in mind. Between the rhythms lies the possibility that cosmic history contains a feature we have not yet mapped. This brings us to the final insight of this subphase. The Hubble tension teaches that the universe may be more connected, more dynamic, and more complex than a single parameter can capture. Expansion is not merely a number, it is a history, and histories contain chapters we have not yet read. We stand within that unfolding story, not at its edge, but inside its momentum. Light carries the memory, structure carries the evolution, the mismatch carries the clue. Insight begins not with an answer, but with the steady recognition of where answers must grow. The universe expands. We follow. And in the space between early and late, knowledge takes shape. The fourth block begins with a return to the sky, not to its mysteries, but to its clarity. Because even when the universe confronts us with paradox, its signals remain steady. Light continues to arrive from every direction, carrying information shaped by time, distance, and the quiet geometry of space. Consider one of the most direct observations in modern cosmology: the way galaxy clusters act as gravitational anchors in the expanding universe. Clusters are massive, holding thousands of galaxies bound together by gravity. Their internal motions reveal how strongly gravity pulls, while the spacing between clusters reveals how quickly space itself stretches. This dual behavior creates an anchor, a direct, observable balance between expansion and gravity. When astronomers measure this balance, they consistently find that the present-day universe is expanding faster than what the early universe model predicts. Clusters are not collapsing as quickly as a slower expansion rate would allow. Their galaxies are drifting apart just slightly more than expected. It is a small effect, but it persists across surveys, instruments, and analytic methods. Now look beyond clusters to the most massive structures known: superclusters and filaments extending hundreds of millions of light-years. These structures form a cosmic scaffolding, an immense interconnected web. Their shapes, sizes, and alignments record how matter responded to billions of years of expansion. Simulations show that if the universe expanded more slowly, these structures would be denser, more compact, and more gravitationally bound. But in reality, they are stretched just enough to match the faster local expansion rate. These observations serve as an anchor. They tie the large-scale universe to the same expansion measured from nearby stars and supernovae. The consistency across scales, from pulsating stars to entire filaments, strengthens the foundation beneath the faster expansion. Shift now to another anchor: the temperature and distribution of hot gas within galaxy clusters. X-ray measurements show how gas settles into gravitational wells. If expansion were slower, gravity would have more time to compress this gas. If expansion were faster, the gas would be more diffuse. Observations again match the faster rate. This repeated alignment is striking. Nothing in the late universe hints at the slower expansion predicted from early light. Every anchor points the same way. Take a visual pause here. Imagine floating in a vast region between two superclusters. Galaxies shimmer in the distance like faint lanterns, scattered across unimaginable distances. Dark matter filaments arc between them like invisible threads. You are surrounded by structures shaped by time and expansion, structures whose scale reveals the universe's recent pace. From this vantage, the faster expansion is not an abstract number. It is written into the spacing of everything you see. These anchors return us to the central fact. The late universe is measured directly. Its expansion rate is read from light that has crossed billions of years of structure shaped by gravity, matter, and dark energy. No projection from the early universe can override this observational truth. But the early universe holds its truth just as firmly. Its temperature patterns are too consistent to dismiss, too detailed to be explained by random error. The slow early expansion remains locked in place. Two truths, two epochs, one universe. Here a subtle reflection emerges. We often imagine the universe as a continuous story, but the tension suggests we are reading two chapters whose connection is not yet understood. The early chapter ends with a specific prediction. The late chapter begins with a specific measurement. What we lack is the missing paragraph linking them. As we stand on the anchor facts of the late universe, it becomes clear that the conflict does not come from present-day observations. It comes from the bridge across time, the way we connect early conditions to modern structures. One more observational anchor deepens this clarity. The cosmic distance ladder, built from parallax and pulsating stars, has undergone independent checks using rare but powerful events like gravitational wave sources. When a gravitational wave signal merges with electromagnetic light, it becomes a standard siren, a direct distance measure. Although sparse, the early standard sirens observed so far lean toward the faster expansion rate, or at least do not contradict it. With more events in the future, this anchor may strengthen significantly. Anchors matter because they tell us where the firm ground is. In the late universe, the ground is firm. Distances, structures, lensing, clustering, and standard sirens all converge. The faster expansion is not fragile. It does not wobble with new measurements. It does not drift. We begin this block with the confidence that one end of the cosmic story is secure. The paradox does not arise from the present. It arises from the mismatch between this present and the past we infer. The late universe expands, quietly and steadily, in a way that is fully consistent with its structures. The early universe expands in a way fully consistent with its radiation. The contradiction lies between, and it is in that narrow space, neither early nor late, where the next insight will grow. We breathe, the universe expands, and the story continues. To understand why the late universe anchors point so consistently toward a faster expansion, we must look deeper into the mechanisms that govern how matter responds to the stretching of space. Not the abstract equations, the physical processes encoded in the movement of galaxies, the heating of gas, the bending of light, and the slow accumulation of structure. Begin with the most direct mechanism, the growth of cosmic structure. Every galaxy, cluster and filament forms from the gradual amplification of tiny early density variations. Gravity pulls matter inward, expansion pulls space outward. The balance between these competing influences determines how quickly structures form and how strongly they bind. If expansion was slower in recent cosmic time, gravity would dominate more fully. Clusters would be denser, filaments thicker, and galaxies more tightly grouped. But observations show the opposite. Clusters appear slightly more diffuse, filaments more stretched, and voids wider than the slower early universe prediction allows. These structural features are not decorative, they are mechanistic fingerprints, direct consequences of how expansion shaped matter. The next layer of mechanism lies in gravitational lensing. When light passes near massive structures, it bends. The degree of bending depends on how mass is distributed, and that distribution depends on how structure grew under the influence of expansion. In a slower expanding universe, lensing signatures would be subtly stronger, more mass clumped in tighter formations. In a faster expanding universe, lensing patterns shift toward a slightly smoother distribution. Modern sky surveys record lensing across millions of galaxies. The pattern aligns with the faster rate expansion. This is not an interpretation layered on top of the data. It is a physical consequence of how matter curves space. Now consider the mechanism behind galaxy velocities. Galaxies drift not only because of expansion, but because of gravitational tugging from nearby structures. These peculiar velocities reveal how strongly gravity competes with expansion. A slower expansion would give gravity more time to accelerate galaxies toward each other, but surveys show peculiar velocities consistent with a universe where expansion has been slightly dominant for billions of years, not merely in the very recent past. This alignment across independent mechanisms is remarkable. Matter, mass distribution, and galaxy motion all point to the same expansion history. Shift now to a different mechanism, baryon acoustic oscillations, the frozen sound waves imprinting a preferred scale across cosmic structure. These waves originated in the early universe, but their apparent size today depends on how much space stretched afterward. The measured apparent size of this cosmic standard ruler aligns with the faster expansion rate. If space had expanded more slowly, the ruler would appear larger, if faster, smaller. Its current size matches the late universe measurements precisely. This convergence demonstrates something subtle. Late universe mechanisms do not rely solely on a ladder of distances. They rely on the accumulated record of how matter has behaved over billions of years. Now turn to the early universe again and examine why its mechanism resists adjustment. There, the dominant process was radiation pressure balancing gravity. Photons scattered off electrons, driving oscillations whose imprints became the temperature patterns in the cosmic microwave background. This process is governed by well-understood physics, particle interactions, density ratios, radiation behavior. The scale of these oscillations determines the predicted expansion rate today, but that prediction assumes no additional components influence the early balance. If something subtle acted only in those early moments, an unknown particle species, a brief burst of early dark energy, a change in interaction strength, the predicted expansion rate would shift, yet most modifications either break other observations or fail to shift the expansion enough to match the late universe measurements. The early universe mechanism is exquisitely tuned. The late universe mechanism is robust across scales. Together, they form a paradox that resists simple solutions. A calm thought experiment helps clarify this mechanistic tension. Imagine a bridge whose shape is determined by forces applied at its ends. One end pulls with a fixed tension, the early universe. The other is pulled by variable weights, galaxies, dark energy, structure, representing the late universe. If the bridge sags more than expected at one end, either the force is changed or the material properties differ along its span. You cannot resolve the mismatch by adjusting only one side. The middle section must be examined. Cosmology is now examining that middle, the long stretch of cosmic history between early radiation and late structure. Another mechanism worth noting is the influence of dark energy. In the standard model, dark energy remains constant, but if it evolved, the expansion history could tilt. A slight shift in the timing or strength of dark energy domination could reconcile the faster late universe expansion with the slower early universe projection. This mechanism requires no dramatic departures, just a more dynamic view of dark energy. Reflect for a moment on a visual scene. Picture a long, slow river winding from mountains to sea. The river's source determines its early speed. The terrain shapes its middle. The ocean shapes its final flow. If the early source and the end flow disagree, the explanation lies in the unseen terrain between them. The terrain is not wrong, it is simply unmapped. Our cosmic terrain, the Middle Era, may contain such unmapped features. Finally, return to the mechanism of time itself in cosmology. Cosmic time is marked not by clocks, but by the evolution of temperature, density, and scale. Each expansion measurement reads a different chapter in this unfolding. The early mechanism reads the opening pages, the late mechanism reads the final ones. The conflict tells us the middle pages hold complexity our current model does not fully capture. We stand in that complexity now. Not lost, attentive. Not confused, observant. The mechanisms are speaking, and their disagreement forms the path to new understanding. A paradox reaches its full shape when every mechanistic detail strengthens the disagreement rather than smoothing it away. By now, the late universe has spoken through structure, lensing, velocities, voids, and the cosmic ruler. The early universe has spoken through temperature patterns, density ratios, primordial oscillations, and ancient light. Both sets of voices are confident. Both describe the same cosmos. Yet their histories cannot be joined without something changing in the middle. This is where the paradox sharpens. Imagine standing at the edge of a long canyon. On one side lies the early universe, carved by the forces that shaped ancient radiation. On the other side lies the late universe, sculpted by gravity, structure, and dark energy. Both walls are stable, smooth, internally consistent. But the canyon between them is deeper than expected. The shapes do not align across the gap. In cosmology, this canyon is the mismatch between predictions and observations. The early universe predicts a certain expansion rate today. The late universe measures a different one. The two should meet at the floor of the canyon, yet they remain suspended above it, unable to touch. The deeper paradox emerges when we consider how tightly these results are held in place. If either measurement had wavered, even slightly, the tension might be dismissed. But the early universe value has remained stable across missions, datasets, and analysis techniques. The late universe value has remained stable across telescopes, distance indicators, and independent cross-checks. Precision has not closed the gap. Precision has carved it deeper. To feel the paradox more viscerally, imagine two clocks measuring the same interval of time. One clock starts at the beginning of the universe, ticking forward through cosmic history. The other starts from the present, ticking backward through observations of nearby structures. If the universe were smooth and unlayered, the clocks would meet in the middle, but they do not. Their hands miss each other by a measurable margin. This is not a calibration error. It is a contradiction in timing, a contradiction that points to something missing in the space between ticks. Now picture a thought experiment. You stand in a quiet observatory dome looking at two projected skies. On one side, the microwave background, mottled with faint temperature patterns from the dawn of time. On the other side, a map of galaxies from the modern universe, glowing in clusters and filaments. Each sky tells a story, each sky is complete. But overlay them, and the story's timelines disagree. The ancient patterns imply a slower early expansion. The modern structures demand a faster late expansion. Two skies, one universe, a single history that refuses to connect. Another layer of paradox appears when we consider the role of dark energy. The early universe was almost entirely indifferent to dark energy. Its influence was negligible compared to radiation and matter. But today, dark energy dominates, driving acceleration. If dark energy has been constant, the transition from early to late should follow a predictable arc, but the arc does not land where it should. Either dark energy behaved differently than we assume, or something else intervened before dark energy took over. This something else becomes the heart of the paradox, not because we know what it is, but because its existence is demanded by the shape of the disagreement. A quiet, emotional mirror forms here. In our own lives, we sometimes reach moments when the past and present do not align. Not due to confusion, but because something changed unnoticed along the way. The universe presents a cosmic version of the same realization. Somewhere in its middle history, a shift occurred that our current model does not capture. The paradox deepens further when we examine gravitational lensing. Lensing confirms the distribution of matter that the faster expansion requires. But if expansion were faster, how did structure grow enough to produce the lensing we see? The early universe would protest. There wasn't enough time, and yet the structures exist, silently contradicting the early prediction. This is not chaos, it is coherence with a missing component. Take a moment to picture the cosmic web again. Filaments stretch across billions of light years, connected like the threads of an unseen loom. Each filament represents the history of expansion woven through the history of matter. Now picture the early universe as a different kind of fabric, a uniform glowing sheet filled with primordial waves. The problem is not that either fabric is wrong, it is that the stitching between fabrics does not match perfectly. Paradox does not emerge from contradiction. It emerges from stitching that fails to align. The final form of this paradox comes from stability itself. The early universe prediction is stable. The late universe measurement is stable. Their disagreement is stable. Stability from all sides produces a paradox that cannot be dissolved by additional precision. The conflict becomes a structural feature of cosmology, and structural features hint at structural insights, or structural revisions. We stand now in the center of this paradox. The universe measures itself in two eras. Those measurements disagree, not by accident, not by noise, but by revealing a space where the laws we use may require new ingredients. A paradox is not a barrier, it is a contour, the outline of something deeper, waiting to be uncovered. We listen to the outline. We stand inside the canyon between early and late, and in that canyon, the next understanding will take shape. Insight comes when the paradox stops widening, and instead begins to reveal its internal shape. By now, the contradiction between early and late expansion rates is no longer a loose uncertainty. It is a fixed feature, a contour carved by data on both sides. From that contour, knowledge begins to rise, not as an answer but as a structured set of possibilities that narrow the search for what the universe is truly doing. The first insight is that the early universe may contain physical ingredients that have so far escaped detection. This is not an extraordinary claim, it is a measured one. The early universe was a plasma of photons, electrons, and matter compressed into extreme conditions. Small deviations in this environment, an extra particle species, a temporary burst of additional energy, a brief interaction that does not exist today, could subtly reshape the cosmic microwave background, shifting the inferred expansion rate downward. This idea gathers strength because it fits the core requirement. Something active early, silent now. The second insight points toward dark energy's history. For more than 2 decades, dark energy has been treated as constant, a smooth pressure that accelerates expansion evenly over time. But the tension suggests that constancy may be an oversimplification. If dark energy evolved, even gradually, the transition between early, slow expansion and late, fast expansion would naturally sharpen. The early universe's prediction would shift downward. The late universe's measurement would hold. The two could meet in the middle. This does not demand exotic physics, only a dynamic form of dark energy, one that changes its behavior as the universe cools. Here a quiet reflection appears. We often assume the universe prefers simplicity, but simplicity in one era may be the echo of complexity in another. Dark energy might not be a fixed quantity, it might be a field with memory. A third insight comes from gravity. Gravity is one of the most well-tested forces, yet all tests occur in limited regimes. We know how gravity behaves in the solar system, we know how it bends light around galaxies, but we do not know with equal confidence how gravity behaves across the entire expansion history of the cosmos. If gravity changed subtly in the early universe, or at very large scales, the inferred expansion could shift. This idea is neither wild nor ungrounded. It reflects a known limitation. The gravitational behavior predicted by our current framework has not been tested in the full range of cosmic environments. Imagine standing inside a vast cathedral. The acoustics near the altar and near the dome may differ in ways that reveal subtle architectural features not visible from the floor. Gravity may have such architectural subtleties. Fourth insight comes from examining the transition period between early and late epochs. The universe passed through several major shifts: radiation dominance ending, matter taking over, structures forming, dark energy eventually accelerating expansion. If even one of these transitions contained unknown dynamics, the expansion history would tilt. A very slight adjustment in that middle period could produce the observed mismatch without disturbing other well-tested predictions. Think of a long bridge whose central section flexes gently under wind. The ends of the bridge remain fixed. The central deflection is small but real. The early universe is one anchor. The late universe is another. The middle may have flexed in a way our model does not yet describe. Another insight emerges from the resilience of late universe measurements. They do not depend on a single method. They rely on a suite of independent observations. Parallax, pulsating stars, supernovae, gravitational lensing, galaxy clustering, void expansion, standard sirens. Their convergence suggests the late universe value is not fragile. It is a stable anchor in the cosmic story. This stability allows us to articulate a paired insight. The late universe is measured directly. The early universe is inferred indirectly. Neither approach is flawed, but inference is more sensitive to hidden influences. This asymmetry matters. A visual pulse emerges here. Picture a calm lake at dusk. A stone dropped near the center creates ripples that move outward. If you measure the ripples far from the center, they carry information about the lake's boundary, depth, and currents. Measure them near the source, and they reveal the initial disturbance. If the distant ripples and the near ripples tell slightly different stories, the difference reveals something about the water in between. The Hubble tension reveals something about the cosmic water between early and late epochs, a region of history that is smooth in our models, but may contain structure we have not yet mapped. A final insight comes from the paradox's stability. Conflicts born of measurement error fade with time. Conflicts born of model limitation sharpen with time. This tension has sharpened. That sharpening is itself knowledge. Hold the last two opposing sentences of this block. The universe has followed a continuous expansion history. Our current description of that history cannot connect its earliest and latest chapters. Both statements are true. Together, they reveal the next step. Cosmology must extend its framework to encompass whatever shifted expansion between early and late times. This does not diminish the standard model, it expands it. We stand in the quiet moment before that expansion of understanding. The universe continues to reveal itself through its disagreement. Light crosses the cosmos with memories of different eras. We listen to both, and in their conflict, insight grows. The late universe holds its anchor. The early universe holds its anchor. The middle invites us forward. We breathe, calm and attentive, as the next questions form. The fifth block opens with a return to the rawest form of cosmic information, the way light moves through expanding space. because expansion is not only a property of distance, it is a property of time. Every photon travelling across the universe carries a timestamp, a record of how space changed during its journey. Consider a single beam of light emitted by a galaxy 1 billion light-years away. As it travels, the universe stretches, the wavelength of the photon stretches with it. By the time it reaches us, the photon has aged, cooled, and elongated. This elongation is measurable, precise, and consistent across the entire sky. It is one of the most reliable facts in cosmology. Light stretches because space expands. Now extend that idea across hundreds of thousands of galaxies at distances ranging from the cosmic neighbourhood to the edge of the observable universe. Each galaxy contributes a piece of the expansion story. Some offer their present-day motion. Some reveal how expansion behaved when the universe was half its current age. Some show conditions from deep in cosmic time, long before our planet existed. When astronomers assemble all these redshift measurements into a single dataset, a coherent pattern emerges in the late universe. Expansion accelerates, distances increase rapidly. Galaxies recede at rates matching the higher expansion value, the same value found through supernovae, pulsating stars, and large-scale structure. The consistency is not superficial. It spans wavelengths, telescopes, and methods. Infrared observations reduce dust effects. Optical surveys collect enormous samples. Radio maps trace neutral hydrogen across cosmic time. Each tool reads the same rhythm. Expansion today is faster than predicted by the early universe. Shift to another anchor. The age of the universe inferred from different methods. If the slower early universe expansion rate were correct, the predicted age of the universe would be slightly older than if the faster late universe rate were correct. Age estimates built from the life cycle of ancient stars, those living fossils in our galaxy's halo, align better with the faster expansion. Stars do not lie about their age. They burn fuel with exquisite reliability, and their lifetimes match the late universe measurement more closely. This is another anchor. Cosmic chronology supports the faster rate. Now consider gravitational time delays, the slight differences in arrival time for light travelling around massive structures. These delays depend on both the structure's mass and the expansion history of the universe. When multiple lensing systems are analysed, the inferred expansion rate again lands near the faster value. These systems are rare, but their precision is high, and their agreement adds weight to the anchor. Pause here for a visual moment. Imagine standing far above a giant cosmic map. Galaxies scatter below like islands of light. Filaments thread between them. Voids open like deep wells of darkness. Every structure moves gently outward, carried by expansion, leaving behind faint trails of shifted light. From this vantage, the late universe expansion is not a hypothesis. It is a pattern, persistent, converging, unavoidable. This brings us to another key anchor, the smoothness of dark energy. Dark energy is uniform. Its influence builds gradually. Because it accelerates expansion, its signature becomes more prominent in the late universe. Measurements of the large-scale distribution of galaxies show that this acceleration has been active for billions of years, not abruptly, not subtly, steadily. If expansion had been slower, the accumulation of this acceleration would look different. Structures would show a different imprint, but they do not. They align with the faster value. Here, a reflection arises. We look at the late universe not because it is easier to measure, but because it reveals the outcome of processes that began long ago. The present is shaped by the entire history of expansion. The structures we observe are the accumulated memory of that history. This is why the late universe is such a strong anchor. It carries not just one measurement, it carries the integrated record of billions of years of cosmic evolution. Another anchor appears when we examine cosmic voids. Voids expand faster than the universe overall because there is less gravity to slow them. Their shapes and sizes reflect the global expansion rate with surprising clarity. Large voids today match the faster expansion, not the slower one. Void expansion is not a subtle phenomenon. It is a clean readout of the universe's stretching. Finally, consider the interplay between expansion and temperature. As the universe expands, the cosmic microwave background cools. By measuring its current temperature with exquisite precision, and combining that with how much light stretches across time, we can infer how much expansion occurred. This method also leans toward the faster rate. Individually, each anchor is modest. Collectively, They form a foundation. The nearby universe expands faster. Its structures reflect this. Its light reveals this. Its clocks agree. Its geometry aligns. This block begins with one clear anchor fact. The late universe tells a consistent story, and that story demands a faster expansion rate. From this foundation, the next sections will explore how the mechanisms that shape this consistency lead directly into the deeper paradox, and the deeper insight that defines the Hubble tension. The universe expands, quietly and endlessly, and the present day speaks with a single, steady voice. To understand why the late universe insists on a faster expansion rate, we must examine the mechanisms that link light, structure, and time into a coherent cosmic record. These mechanisms are not theoretical ornaments, they are physical processes unfolding across billions of years, each one leaving an imprint we can measure. Begin with the mechanism of redshift itself. When space expands, light stretches. This stretching is proportional to the cumulative expansion the photon experiences along its path. The farther the light travels, the more it stretches. This relationship allows astronomers to convert a photon's color shift into a measure of the universe's growth. If expansion were slower in the last several billion years, photons arriving from moderate distances would show smaller shifts, but they do not. Their shifts are larger. They indicate a universe that has been expanding more rapidly than the early model predicts. The mechanism is direct. Light carries expansion in its wavelength. Now consider how distance is tied to brightness. In an expanding universe, more distant galaxies appear dimmer, not only because they are far away, but because expansion stretches the light, reducing its energy. This dual dimming, geometric and cosmological, is built into every measurement of supernova brightness. When astronomers map the brightness of thousands of supernovae to their redshifts, they trace the shape of the expansion curve. A slower expansion rate would create a different curve, one with less bending at moderate distances. Yet the observed curve shows strong bending, a signature of late-time acceleration, and a faster, present-day expansion. This curvature is not interpretation. It is geometry in motion. Next, look at the mechanism behind baryon acoustic oscillations in the late universe. These structures originated as sound waves in the early cosmos, but their apparent size today depends on how much space stretched between then and now. Imagine a ripple frozen into a vast cosmic fabric. As the fabric expands, the ripple expands with it. By measuring the apparent size of this ancient ripple at different distances, astronomers reconstruct how expansion evolved over time. The ripple size today is smaller than it would be under a slower expansion scenario. This means the universe has enlarged the space between galaxies more rapidly than predicted. In this way, a tiny feature imprinted billions of years ago becomes a mechanistic probe of the modern cosmos. Shift to another mechanism, the growth of cosmic structure. Structure grows when gravity slows the expansion locally, allowing matter to clump. If expansion were slower in the late universe, these clumps would grow more efficiently. Clusters would be more massive, filaments more pronounced, void boundaries sharper. But observations show slightly undergrown structures relative to the slower rate prediction. They look exactly as they should in a universe where expansion has been strong enough to resist full gravitational collapse. It is a delicate interplay. Gravity tries to gather, expansion tries to separate. The result preserves a detailed record of expansion history. Now consider gravitational lensing, which bends light around matter. The amount of bending depends on how clustered the matter is, and clustering depends on expansion. If expansion were slower, matter would cluster more strongly, producing slightly more lensing. But the measured lensing patterns indicate less clustering, the signature of a universe that has expanded too briskly for gravity to keep up. Lensing is not a symbolic measurement, it is the direct curvature of space, and it reflects the faster expansion. Another mechanism arises from galaxy velocities. Galaxies do not simply drift apart at the expansion rate, they also move under the influence of nearby structures. These peculiar velocities reveal the strength of gravitational competition with expansion. If expansion had been slower, galaxies would have more time to accelerate toward one another. But surveys show motions consistent with a universe where expansion dominates more strongly than the slower rate model allows. In this way, galaxy motions become timekeepers of expansion. A quiet reflection. The late universe is not a single measurement. It is a network of interconnected mechanisms, each responding to expansion in a different physical way. If expansion were slower, all these mechanisms would shift together, but they do not. They shift in lockstep toward the faster value. Yet the early universe remains equally disciplined. Its mechanisms, acoustic peaks, radiation density, temperature variations, converge on the slower rate with unwavering precision. The two mechanistic systems, early and late, disagree consistently, not randomly. A thought experiment clarifies this mechanistic divide. Imagine two rivers feeding into a single lake. One river carries cold, fast-moving water. The other carries warm, slow-moving water. If the lake's temperature and motion match the cold river, the warm river must have changed upstream. If the lake matches the warm river, the cold river must have changed. If neither fully matches, something in the lake itself, currents, depth, hidden channels, must be influencing the flow. Cosmic expansion behaves the same way. The early universe sets one flow, the late universe sets another. The middle must contain a process, subtle but real, that shifts the expansion from one regime to the other. The mechanisms speak clearly. The late universe carries cumulative evidence of faster expansion. The early universe carries cumulative evidence of slower expansion. Between them lies the process that cosmology has not yet mapped. As Block 5 continues, we will follow these mechanisms toward the center of the paradox, and toward the deeper insight that may resolve it. We breathe. The universe stretches, and its mechanisms reveal the space between prediction and reality. A paradox deepens when every mechanism that should clarify the universe instead reinforces its disagreement. By now, the late universe has offered a consistent account of faster expansion through redshift, brightness, lensing, structure growth, void sizes, and cosmic chronology. The early universe has offered an equally consistent account of slower expansion through primordial oscillations, density ratios, and temperature patterns frozen into ancient radiation. Both accounts are complete, neither bends, and this is precisely where the paradox achieves its full shape. To grasp this clearly, picture two vast maps drawn from opposite sides of time. One map is traced by ancient light, smooth, precise, detailed in its own language. The other is traced by modern structures, textured, complex, built from billions of years of cosmic evolution. Each map is internally perfect. Each describes the same universe, but when placed side by side, the contours do not align. A subtle mismatch becomes a structured contradiction. Imagine holding two transparent layers, each with a drawing of the same coastline. One layer captures the shoreline as it appeared thousands of years ago, smooth and continuous. The other layer captures the modern coastline, eroded, reshaped, more jagged. If you overlay the layers, they should align after accounting for known forces, but if they do not, the discrepancy indicates a missing process that reshaped the land, not an error in the layers, a change in the world between them. The Hubble tension is such a discrepancy, a sign of a reshaping not yet accounted for. The paradox grows even sharper when we consider how contradictory forms of evidence correlate internally. The early universe's slower expansion rate emerges from acoustic peaks in the cosmic microwave background. These peaks depend on the density of matter, radiation, and the ratio between them. If any of these parameters were misestimated, the peaks would shift, but they don't. They lock the slower value in place. Meanwhile, the late universe's faster expansion arises from distance indicators, void expansion, structure formation, and lensing. If any of these were compromised, their derived expansion rate would shift, but they don't. They converge on the same faster value. This dual rigidity produces a paradox that is unusually resilient. To see this tension more vividly, imagine two musicians performing a duet across a vast distance. One plays the opening notes, slow, deliberate, echoing the early cosmos. The other plays the concluding notes, faster, bright, shaped by acceleration. If the universe were completely understood, the melody would flow seamlessly from one musician to the other, but the transition between their performances is disjointed. The notes do not match at the seam. Yet neither musician is wrong. Both follow the score given to them. The missing notes lie between them, in the portion of the score that no one has yet recovered. A deeper paradox emerges when we examine how structure growth interacts with expansion. If the early universe's slower expansion were correct all the way to the present, structures would have had more time to form. The cosmic web would be denser, lensing would be stronger, clusters would be more massive. But they are not. Their properties match a universe with faster late-time expansion. This means that the early universe prediction does not simply disagree with the late universe measurement, it disagrees with the entire late universe environment, the distribution of galaxies, the gravitational landscape, the spacing of cosmic features. Taken together, the disagreement becomes geometric as well as numeric. Pause for a moment. Picture floating in intergalactic space where galaxies drift silently and the cosmic microwave background glows faintly from all directions. Ancient light arrives with the rhythm of a slow, early expansion. Nearby structures drift with the rhythm of a faster, modern expansion. You are suspended between tempos, hearing both at once. Neither dominates, neither fades. The dissonance is calm, precise, and unmistakable. Another layer of paradox arises when we compare how each side of the tension responds to effort. When researchers try to lower the late universe value through reanalysis, recalibration, or added uncertainties, the value remains stubbornly high. When researchers try to raise the early universe value by adjusting parameters or allowing for hidden components, the value remains stubbornly low. Each side resists efforts to force agreement. This resistance signals something fundamental. The paradox is structural, not incidental. Imagine a long metal beam tested for stress. Press on one end and it bends predictably. Press on the other and it bends in the opposite direction. But if you press on both ends and the middle remains rigid, the rigidity reveals a hidden property of the material. The Hubble tension reveals such rigidity in cosmic history. One more level of paradox appears in the nature of the gap itself. The difference between the two expansion rates is not enormous. It is around 10%. Small in everyday terms, huge in cosmic terms. A small difference in expansion, compounded over billions of years, leads to galaxies ending up millions of light years farther apart. This means the mismatch is not an aesthetic issue. It is a geometric one. Two expansion histories lead to two different universes, yet only one universe exists. This is the heart of the paradox. The universe we observe today cannot be reconciled with the universe we infer from its earliest light, unless something in its middle history is missing from our model. A final image brings the paradox into focus. Imagine a long bridge fading into morning fog. You can see the first span clearly. That is the early universe. You can see the last span clearly. That is the late universe. But in the fogged middle, something shifts the alignment just enough that the spans no longer meet. The paradox does not accuse either anchor. It highlights the fog in between. We stand inside that fog, calm, attentive, listening to the universe disagree with itself in a way that reveals the boundaries of our understanding, and those boundaries outline the space where new physics may live. Insight grows when a paradox stops feeling like a contradiction and starts revealing its internal logic. By this point, the disagreement between early and late expansion rates is not a loose thread. It is a defined boundary, a boundary that shows where our understanding is complete and where it is not. Knowledge emerges by tracing that boundary carefully. The first insight in this final subphase of Block 5 is that the tension isolates a specific portion of cosmic history. The early universe is well understood. The late universe is well measured. So the missing ingredient must lie between them, in an era neither too hot nor too cold, neither too dense nor too diffuse. An era where new or subtle processes could operate quietly, leaving only faint traces in the expansion profile. This middle region spans the first few 100,000 years to the first few billion, a broad stretch, yet one whose physics is not fully mapped. We know the major transitions: plasma to atoms, atoms to structure, structure to acceleration. But it is within these transitions, not at their endpoints, that new physics could hide. The tension singles out a specific portion of cosmic time as the place where our model requires refinement. A second insight concerns the role of unknown particles or fields. The early universe was sensitive to even the slightest amount of additional energy. A small population of lightweight particles, or a weakly interacting field, could alter the early expansion enough to shift the inferred Hubble constant downward. These components would need to fade or transform later, leaving the late universe unchanged. This idea gains strength because it fits the required structure: early influence, late silence. Some proposals include sterile neutrinos, light relic particles, or scalar fields briefly active during the early plasma era. None are confirmed, But the insight is not about choosing one. It is about recognizing that any such component would reshape the early expansion without disrupting the late one. Early-only physics can reconcile ancient predictions with modern measurements, pointing towards subtle additions to the cosmic inventory. A third insight examines dark energy with fresh perspective. Dark energy dominates the late universe, not the early one. If dark energy evolved, even slowly, the expansion curve would shift. A slightly weaker influence earlier and a slightly stronger influence later could create the observed discrepancy. This does not require rewriting physics. It requires allowing dark energy to have a history. The insight grows from a simple realization. Our assumption of perfect constancy is not dictated by evidence. It is chosen for simplicity. Dark energy may not be fixed. Its evolution could create the bridge between the two expansion regimes. A fourth insight appears when we consider gravity itself. Gravity is the oldest known force and the least understood at cosmic scales. If gravitational strength or behavior shifts under extreme conditions, high density, large distances or low accelerations, the inferred expansion history could shift as well. Modified gravity theories already exist, but most are constrained by solar system tests. The universe, however, contains conditions far beyond such tests. Gravity might behave differently across cosmic time, in ways that influence expansion without disrupting galactic behavior. This idea is subtle, but the insight is simple. Gravity may have a time-dependent or scale-dependent character that our current framework does not include. A quiet reflection emerges here. We tend to assume the laws of nature look the same everywhere. But the universe is vast enough that this assumption, while elegant, is not guaranteed. The tension invites us to consider that the laws may be more flexible than we have imagined, not broken but textured. Next, consider what the tension teaches about observation itself. The early universe is inferred indirectly, from patterns in ancient light shaped by model assumptions. The late universe is measured directly. Distances, brightness, structure, lensing. This asymmetry does not weaken either side. It explains why the early universe may be more sensitive to hidden physics. Inference is more vulnerable to missing ingredients than direct measurement, identifying the early universe analysis as the most likely site of incomplete modelling. Another insight emerges from the stability of the paradox. When a conflict persists across growing precision, it suggests the underlying model is near the edge of its applicability, not broken, simply stretched to its limits. Imagine a map that works flawlessly within one region, but becomes inaccurate at the border of another. The border is not failure, it is instruction. A hint that the map must be extended. The persistence of the tension signals a boundary of the standard cosmological model, not a flaw, but a frontier. A visual moment clarifies this. Picture a vast sheet of fabric woven with ancient and modern threads. The ancient threads run straight and uniform, representing primordial physics. The modern threads twist through filaments, structures, and accelerating expansion. Where the two thread sets meet, the weave distorts slightly. The distortion is not damage. It reveals how the fabric transitions between eras. The tension is such a distortion, subtle, persistent, meaningful. A final insight comes from the broader scientific context. Cosmology has grown through a sequence of such tensions. The mismatch between starlight and nuclear physics, the galaxy rotation problem that hinted at dark matter, the unexpected acceleration that revealed dark energy. Each tension opened a door. Each door led to new understanding. The Hubble tension fits that lineage. Hold two sentences that capture the knowledge gained. The universe is consistent in the information it provides within each era. The universe is inconsistent in the way those eras connect under our current model. Both are true. Together, they describe where new physics may arise. We stand on the edge of that newness, calm, alert, watching the universe reveal itself not through agreement, but through disagreement that forms a path toward deeper comprehension. The middle of cosmic history holds the key. The tension indicates where to search, and the insights of this block show how that search might begin. The universe stretches, quietly and endlessly, and in the space between early and late, knowledge continues to grow. The story of the Hubble tension ends not with resolution, but with direction, a quiet recognition that the universe is telling us more than we first understood, and that disagreement in its signals is not failure, it is information, waiting to be interpreted. Across this documentary, two expansion rates have stood side by side. One emerges from the earliest light, shaped when the universe was young, dense, and nearly uniform. The other emerges from galaxies, structures, and gravitational patterns in the modern cosmos. Both are stable, both are precise. Both describe the same universe in different eras, and the numbers refuse to match. This mismatch is the heart of the Hubble tension, a slow, early expansion, a fast, late expansion, a model in between that cannot reconcile the two. But rather than weakening cosmology, the tension strengthens it, because when two independent truths fail to meet, the space between them becomes the frontier of discovery. Pause for a moment and imagine the timeline of the universe stretched out before you. At one end, the first atoms form as ancient light escapes. At the other, galaxies drift apart under the pull of dark energy. Between these ends lies a span of cosmic history more than 13 billion years long. Most of that span is invisible to direct observation, yet it shapes everything: structure, motion, temperature, the geometry of space itself. The Hubble tension points directly into that invisible span. It says, something happened here, something subtle, something real. Maybe a brief burst of early dark energy. Maybe an unknown particle species. Maybe gravity behaving differently under extreme conditions. Maybe a transition in cosmic structure we have not yet mapped. Whatever the answer, it will refine, not replace, our understanding of the universe. Knowledge grows from such tensions. Dark matter emerged from a mismatch. Dark energy emerged from a mismatch. Now, another mismatch stands before us, calm and persistent. We do not yet know what fills the gap between early and late expansion, but we know exactly where to look. And that clarity, that narrowing of the search, is itself profound progress. As the universe continues to expand, quietly and endlessly, its two rhythms continue to echo across time. One rhythm from the dawn, one rhythm from the present. In their disagreement, they form a doorway, and walking through that doorway is how we will learn what the universe has been hiding in the long, middle chapter of its history. The cosmos stretches. Light carries its memory. We listen, and the next discovery waits in the space between.